So today we would like to relate the phase margin to the system parameter for the second order system. In particular, we would like to relate the phase margin to the to zeta, which clearly, if you relate it to zeta, it means that in the time domain, there's a relationship between the phase margin and how much overshoot you will be tolerating in your system. So in order to establish this relation, this is the standard second order system. Okay, so the open loop system is given by, this is the open loop system. Okay. Well, in the frequency domain, we will have G H of J omega equal to omega n square J omega plus zeta omega n. So what's the magnitude? What will be the magnitude in here? What will be the magnitude? Any thoughts, Shabab?
Yes, the magnitude will be omega n square over root
Omega
and then multiply by root omega square plus 4 zeta square omega n square.
And the angle, the phase will be
minus tan inverse, minus 90 minus tan inverse omega over 2 zeta omega n.
Thank you, Abdurrahman. طيب.
Welcome.
Majid al-Harthi. How do I obtain the phase margin? I would like to obtain the phase margin for the system. So how do I proceed?
phase margin كنت بسألك عنه بداية الكلاس دكتور.
كيف؟
I'm not sure how to get the phase margin.
Okay, let's Jasim.
ايوه دكتور.
How do you get the phase margin?
والله ما فهمت الكلاس اللي ماضي.
Any volunteer?
We need to find the crossover frequency.
So first of all, we have to find the gain crossover frequency. That's basically, we will set the magnitude equal to 1. That will give us the gain crossover frequency. We use the gain crossover frequency to substitute in the phase, and that will give you the phase at the gain crossover frequency you subtracted from 180, or you added to 180. Okay. So basically, this is what we have, and this is the gain. You set the gain equal to 1. And now we will solve for omega, which will satisfy this equation. This equation is nothing more than, equating the magnitude, okay, the magnitude equal to 1. And this is the way we define the gain crossover frequency. So once I solve this equation, okay, I can normalize it to omega n. So the phase crossover frequency is going to be function in a way of zeta in this sense. Now, the phase margin is defined, you find the phase, and then how can you go to the 180 degree? That's basically, if you remember, if I have a system like this is the -1. Okay, we said this is the Okay, sorry. This is the point which we get. This is omega g, which we obtain from this equation. We substitute in here and to get this phase, okay? Then how much I need to go to the 180 degree? So the phase margin equal 180 minus the phase of the system evaluated at omega g. Through the trigonometric identities, I can reduce this equation into this one. So now I have a relationship between the phase margin and zeta. This equation is a little bit complicated, so people will, do approximation. If we do the approximation, this is basically what we are going to get. The zeta, the damping factor, okay, equal 0.01 times the phase margin, where the phase margin given in degree, not in radian. This is the approximation. And this is very important. When we go to the design, usually they will ask you to satisfy certain, phase margin. Okay, so if you have second order system, you can relate the phase margin directly to the damping factor. So now you have a sense of, okay, if I increase the, damping factor, what will happen to the overshoot in the system? If I increase the phase margin,
the damping factor will increase.
The what?
The damping factor will increase.
Okay, which means that the oscillation, what will happen?
Will be killed.
It will be
damped.
Reduced.
Reduced.
It will be reduced. Okay.
But I think, Doctor, we didn't touch this.
صوتك مو واضح كثير يا عبد الرحمن.
Now it's clear, I think.
Okay.
Yes, I think didn't touch the topic of, or the idea of the quality factor.
What do you mean quality factor?
Quality factor, it is defined for the system. It is a parameter defined for the system that measures the quality of the system, taking the input zeta and the parameter. It's for the second order system, because the operational amplifier, it is modeled using a second order system.
Well, look, the quality, it depends on how do you define it. Okay, so how do you define it? What do you want from your system? Okay. Well, there are many topics we cannot cover. Definitely, we cannot cover everything. But at least, we know what's important to us is, how much oscillation in the system, how big the oscillation, whether the system is stable or unstable. Okay, if the system is unstable, how do I stabilize it? Okay, we are going to do later on the compensator or controller, and they are, some of them based on lead lag compensator. And the lead lag compensator, they need the idea, this idea which we are talking about. They need the idea, they based on the phase margin of the system. Okay, but definitely there are many sensitivity. We are not taking sensitivity. Okay, so because look, you have limitation in the course how much you want to teach. Okay, thank you. Any other question or comment? Okay, now let's do the same. The phase margin and gain margin concept. However, it's based on the body plots. We are not going to define anything new. Okay. but we can obtain the gain margin and the phase margin using the body plots. Okay. Well, so far, if you remember, from the Nyquist, okay, if I need the gain margin, I'll find this frequency, find the magnitude, and see how far I'm from the -1 point. Okay. معاذ العتيبي.
ايوه دكتور.
Okay. Now, how do I define, okay, what does it mean, okay, to have, certain gain margin? What is gain margin? What's the meaning of gain margin? Shabab, I just want you to be involved in the lecture. It's not, it's not an exam. I'm not, I'm not grading you on this one, but I just want to make you, everybody, be with us or in what we are doing. Well, any help, Shabab?
Yes, Doctor.
النمر wait عبد الرحمن النمر مرتضى النمر ولا العامر sorry العامر.
Yes.
Okay, what does it mean? Phase gain margin or phase margin. What is the gain margin?
The margin in which the system is stable.
So basically, when we talk about gain margin, it means that how much I can add more gain. Okay, so suppose the gain at this point we can evaluate. So what is the factor? I will be multiplying this point to bring it to the -1. This is the gain margin. Okay, the phase margin, okay, again, if this is the -1, I will intersect the unity with the locus and find omega, okay, g, where the gain equal to 1. Evaluate the angle, which is this one. Then how much you need to go to the 180 degree. This is the phase margin. I want to do the same concept and relate it to the body plot. Okay, so first of all, we will be talking about in here the body plot. One of the drawbacks from body plot, we have to work with the minimum phase system. Minimum phase system where the poles and the zeros are in the left half a plane. That's basically if I have, let's say, S minus 10 over S plus 1, S plus 7. This is non-minimum phase because the zero, even though it's stable, okay, but this zero, it causes certain behavior on the system. And body plot usually will be, addressing system where they are minimum phase, where all the poles and the zeros are in the left half plane. So minimum phase, the open loop system is stable. Open loop is stable, but it is not necessary that the closed loop is stable. Okay, again, now we will define the gain crossover frequency. Okay, so if you are talking about body plots, this is the, okay, in the body plot, I have two plot. One is the, okay, let's say, okay, so suppose I have, and this is the 20 log of the magnitude, and then I have the phase in here. Suppose this is what we have for the phase. Okay, so the gain crossover frequency, what's correspond to which point in the body plot in the magnitude is correspond to this point?
It is corresponding to the 0 dB.
Exactly, because I take 20 log of this one, 20 log 0 will be 20 log 1 will be 0. So I'm looking into this point. This is my gain crossover frequency. The phase crossover frequency
minus 180.
So basically, it's correspond to, let's say, this is the minus 180. I will take the intersection here and I will read the frequency. So look, finding the gain margin, phase margin, if we have the body plot ready, it is very simple. Okay, the gain margin again is defined the change in the open loop gain required to make the system unstable. While the so basically, if we are talking about again the body plot, okay, I will take the, to find the gain margin from the body plot, I will find the magnitude at the phase crossover frequency and how much I have to add to it to bring it to the 0 dB line. While the phase, I will get the gain crossover frequency, read the angle, and add it to 180 degree. So let me do it graphically. So what I have in here, the upper graph represents the magnitude, okay? While the lower graph represents the phase. So let me now, on all those graphs, let me define the gain crossover frequency and the phase crossover frequency. Okay. So if you have the graph, this is the 0 dB line. I will find the intersection of the 0 dB line with my graph. And I will read the frequency. This is the gain crossover frequency. Any question here? So if you have your graph, if you have the body plot, just take the intersection of the plot with the 0 dB. While the phase crossover frequency, okay, I will take I'll look into the graph and then locate where is the minus 180 degree and then get the graph intersected with your graph. And that will be the phase crossover frequency. Any question? So now I need to find the phase margin, the gain margin.
So the gain margin will be the difference between, or that derives actually, that makes 180 exactly below 0 dB. Minus 180 exactly below 0 dB.
Yes. So look, let's start with the phase margin. I will read, this is the gain crossover frequency. Go down, read in the intersection, find the angle, find the phase. Then how much you need to go to the minus 180 degree. And this is basically the phase margin. Okay. The gain margin, I will take the phase crossover frequency, take vertical line, intersect it with the gain and read the gain. Then what is the difference between this reading and the 0 dB? And that will be your gain margin.
Because when we have 0 dB and minus 180, the system is unstable, right, Doctor?
Yes, the stability version, yes. And this is the way we define to start with the gain margin and phase margin. How much gain add to the system until it becomes unstable. So this is, again, related to the Nyquist. This is the -1, and I'm taking this point. How much I can go in here. This is correspond to how much I will go between this point and this point. While the phase margin, okay, again, this is -1. This is correspond to this point, the frequency, okay. Sorry, for the phase margin, okay. This is correspond to this point. The gain equal to 1. The 0 dB, go down. Read, and how much you go to the 180 degree. Any question here?
Doctor,
Yes.
the gain margin tells us how much we can add gain.
Yes, exactly.
But for the phase margin, how can we add phase? We didn't. I cannot imagine how can we add phase to the system.
Well,
We can only add gain.
yes. The gain very clear. You multiply by something.
Yes.
Okay. Your question is valid. We will definitely discuss it in the compensator, but simply look, this is what you do. Suppose I have a system in here. Okay. This is G of S. And suppose I have another system here called S plus A, S plus B. Okay. Now, if let's focus on this function G of compensator, let's call it, of S equal to S plus A, S plus B. So G C of J omega equal to, okay, what does it equal to? J omega plus A, J omega plus B. What will be the angle? Let's forget. Okay, let's forget about the gain, because the gain you don't have any problem with it. What will be the angle? What is the phase? So this is the angle of tan inverse of omega over A minus tan inverse omega over B. Do you agree?
Yes.
A and B, look. Let's say this is this is A, this is 0, and this is B, let's say. Okay, this is I'm adding a 0 and a pole. Okay, if I need tan inverse of omega over A greater than tan inverse of omega over B, okay, which value of A and B will do the job for me?
A has to be smaller than B.
A is smaller than B, isn't it?
Yes.
Okay, so I'm in A near the J omega axis, and A and B is farther. So the net in here, what do I get? The net of this one is going to be a positive phase, isn't it?
Yes. Yes.
Okay, so this phase will be added to the system. While if you have the other way around, if B is smaller than A, it means that the phase is negative, and I'm subtracting, I'm taking away some phase from the system. Okay?
Okay.
Is it clear?
Yes, it's clear.
Okay, so the way to do add the phase, we will come to it. We will discuss it in detail because this is, you know, this is where we will do the design.
By the way, Doctor, the first two questions is about what you are explaining right now.
Okay. Yes, in the homework?
Yes, in the homework, yes.
Okay. Now, let's discuss the stability. Okay. This is another summary of what's the procedure. Okay. Quickly, okay, draw a line, vertical line, okay, through the 0 dB and through the 180. This is the gain crossover, this is phase crossover. Draw horizontal line and read, this is the gain at the phase crossover frequency, and this is the phase at the gain crossover frequency. And then you will have the gain margin, this is the gain margin, and this is the phase margin. Okay. Now tell me, based on what you see in here, when do you think the system will be stable?
The system will be stable when when the gain is less than 0 and the phase at the same time is minus 180 or less. It is a scenarios, Doctor. But the most important thing is that the 0 dB and minus 180 should not lie above each other, or we shouldn't have a positive gain and minus 180 or yes, a minus 180 phase.
So look, what you are saying is absolutely correct. This is, look, I need the gain margin. I need my gain margin in this area. Why this area? Because look, suppose in here, the magnitude is going to be in negative, isn't it? In minus, okay, so let's say I have in here, this is minus, okay, 20, minus 20. So 20 log of the magnitude equal to what? Minus 20. What will be the magnitude?
0.1.
It's going to be what?
0.1.
0.1. Exactly. Okay, 0.1. Think about it. In the Nyquist, this is the minus 1 and this is 0.1, which means that, you know, I'm not encircling the minus 1. Okay, so my system will be stable. Okay, we will come in a moment, but I just want to point out, and again, what you have said, Abdurrahman, absolutely correct. So we need, for this to be stable, the gain margin in this area. The same thing, the phase margin should be in this area. That is above the minus 180 degree. What?
أقول الكويز بيكون متى دكتور؟
الساعة كم الحين؟
ونص.
We still have 5 minutes. No, I'm putting my timer. Don't worry. We will, okay. So the stability from body plot. The stability from body plot, we will look into the open loop gain of less than 1, or the gain margin, okay, is positive. The positive in the sense it is less than the 0 dB. It will be oscillatory if I precisely at the 0 dB. At the 0 dB, it means that I'm on the minus 1, or I'm at just the, you know, on the, my pole are on the, j omega axis, and my system will be start oscillating. And definitely, if the gain margin greater than, okay, it's positive that above the 0 dB line, the system becomes unstable. Okay. Let's take, for example, in here. This is, we'll explain it. I have, this is the, okay, magnitude curve, and this is the phase curve. Let me get the, okay, to determine the gain margin, I'll determine this frequency, this point, and this is the frequency, the phase crossover, and I go and read the dB. If I am intersecting below the 0 dB, it means my system is stable and my gain will be, gain margin will be positive. Okay, the same thing for the phase. The same thing for the phase. I will read from here, go down, take this intersection. If I'm above the 180 degree, then my system has a positive phase margin and the system stable. While this is in here, at the 180, I'm intersecting at this point below the 0, above the 0 dB line, sorry, which means my system has become unstable, or the phase margin in this area. Okay, I will go again back to this example next time, but now I want to give you the time to prepare your quiz. Okay? So the quiz will start within a couple of minutes. Good luck. Well, the quiz is the same. This is warning, Abdurrahman, or what? The quiz is going to start, or what?
ما هو عندي هذا دكتور، ما ادري مين اللي فتح المايك.
هو بس ما سبحان الله انا I don't know ليش عجل سوري. طيب. So please put on your camera, please.
دكتور هو الكويز بيكون في شو اسمه؟ بيكون في تحت الكويز برضه نفس الكلام صح؟
اي نعم same setup نفس الشيء. اوكي.